Good morning, everyone. Welcome to the lectures on quantum mechanics. Our main reference for the lectures is the book titled Introduction to Quantum Mechanics by David J. Griffiths. Most materials in this lecture are taken from that book, and I recommend you to buy the book. So for our first chapter, we will discuss about wave functions. And of course, this wave functions can be derived from the Schrödinger equation. And we will discuss that as we go through the lecture. So first of all, let's look at this particle with mass m. And this particle or this object is constrained to move in one direction along the x-axis. And this moves because of the force f of x here, which is a function of position and time. Classical mechanics is able to determine its position at a given time by using the second law of Newton. And when the position is determined, it can also determine its velocity, the momentum, and as well as the kinetic energy of the particle and any other variables you want to measure. So here you have Newton's law. You can apply F is equal to ma, mass times acceleration. The acceleration is just the second derivative with respect to time of the position. And this is just equal to the negative differential of the potential with respect to space. In this case, x. The potential usually for conservative systems is just a function of space. So that's why you have only here space derivative. With appropriate initial conditions, typically when you start the system or when you start the experiment, you always have that t equals 0. That's your initial state, the state of your experiment. So that's your t0, and the state variables would have to be defined at that time. That's the initial conditions of your experiment, and then you can determine the variables, in this case the position at later time t. In quantum mechanics, on the other hand, approaches this problem in a different way, because we have to know the wave function of the system or the particle or the object. The wave function is usually denoted by psi, psi, which is a function of space and time of the particle. And then we solve the Schrödinger equation, this one, to be able to get the wave function. Here you have the wave function, and on this side you also have the wave function here. The Schrödinger equation is just I h bar partial differential of psi with respect to time. This is equal to negative of h bar square over 2m, second order partial differential of psi with respect to space, plus the product of the potential times the wave function. The potential here gives the constraint of the system. So you have this side equal to this side. This side is a differential with time, and this side is a differential with space. The I here is just equal to square root of -1. H bar is the reduced Planck's constant. The V is the potential, as I've said earlier. M is the mass of the particle or the object or the system. By the way, we don't talk about magnetic forces here, and this lecture assumes that um, the particles are moving in less than the speed of light. Here is the value of the Planck's constant, the reduced Planck's constant. It's 1.05453 times 10 to the -34 joules second. Or you can just simply write it as h bar. The Schrodinger equation here, you have to remember as a physics student, at least you have to remember this equation. IH bar, partial differential of psi with respect to time, is equal to negative h bar square over 2m, second order partial differential of psi with respect to space, plus the potential times the wave function. The Schrodinger equation is logically similar to Newton's second law because it can define your wave function, and then from that wave function, by having again an initial condition or initial conditions, you will be able to find its wave function at a later time, just like determining the position at a later time in classical mechanics. So the wave function can be used to get some variables at a later time in your experiment, in the variables of interest in your experiment, I mean. So what really is the wave function? Or what does it do when you have it? The particle in classical mechanics is localized at a point. You can see a particle like it's there, it's at one point, but the wave function spreads out in space. It's all over, and it's a function of space and time. So it's a particle which is a different entity, and its equivalent wave function, which is also a different entity but spreads out in space. So how can the wave function describe the state of a particle? According to Max Born, the Born statistical interpretation is that the square of the wave function here gives the probability of finding the particle at x, at position x, in time t. By the way, the square of the wave function is just the conjugate of the wave function, the complex conjugate of the wave function times the wave function itself. This can also be the wave function times its conjugate. It's commutative, meaning it can interchange. This one assures you that the probability is real and non-negative. So here is an example of a wave function here. So if you put this wave function in a particle experiment, you have here the positions of the particles at some time earlier. The position of the particle is here, and at some time it goes through this kind of wave-like um, uh, fashion. So at some point A, it has to be here, and at some point B, here, and at some point C in this area. So the particle is most likely to be found at this point A, and zero probability to be found in B or at this point. But if you find a particle, if you measure the particle, it's the probability of finding the particle here is less than that of A. But it's of course greater than finding the particle here at B. This is a typical wave function. So the wave function could be like the wave function of the hair strands on your hair. So like for example, when you were born, you have few hair strands. And then when you are growing up, more hair strands grows on your scalp. And then at some point, you have to sport a hair that's shaven. So you have to this part represents that. And then there came a point that you have to have your hair grow freely. Then you have more hair strands and you have thick hair at this point. So that's kind of a wave function also of your hair. It could also, the wave function could also represent your financial status. So it could be anything you want to measure. So here, the shaded area in this particular plot. By the way, this plot is, you have the y-axis as the size square, and then in this, the horizontal axis is the position, for example. It could be time as well, could be other variables. So the shaded area represents the probability of finding the particle in this range, this range. So imagine that everything under this curve is the probability, and this part is just the probability of finding the particle in this um, position, in this range of position, very small. So the statistical interpretation of Max Born introduces the indeterminacy into quantum mechanics. You wouldn't know exactly where the particle is, but you know that the particle is represented by a wave function. Then of course you can get some values if you do some operations in quantum mechanics. By the way, intend, I don't intend to let you understand fully or completely quantum mechanics. It's difficult. Quantum mechanics is difficult, but we would just like um, we would just my objective is for you to just do quantum mechanics, to be able to do quantum mechanics, not really understand, but in doing the operations, the processes in quantum mechanics, you'll be able to understand quantum mechanics. In this case, in this lecture, or in the future lectures, we will just do quantum mechanics, not really understand quantum mechanics. We will do, and then by doing it, we'll be able to understand, or if not, uh, uh, it will uh, increase our curiosity in understanding quantum mechanics. So that's a wave function. That's an example. This is an example of a wave function. So again, in this example, the particle is likely to be found in A. because it has a high probability, because psi square is proportional to the probability, and um, it's unlikely to be found here at B. I mean. So again, psi x of t, I mean psi xt, this this is just to let you know that the wave function is a function of space and time. You square that times dx. This is a very small number, infinitesimal, in that range. That is equal to the probability of finding the particle between x and x plus d at time t. So let me just read this. The outcome of an experiment to measure a position is not predicted with certainty in quantum mechanics, but it offers the statistical information about the possible results. Say, for example, if you put your hand in front of your face, of course, your hand will be in front of your face, but your hand will be shaking or your fingers will be moving. So there is some kind of uncertainty, but your hand is still in front of your face. Now, suppose the position of a particle was measured and it was at point C. The question is, where was the particle just before the measurement was made? In this case, you have three positions or three plausible answers to the question. There is a realist's position that the particle was at C. It was at C before the measurement. And then you have an orthodox position that the particle was not really anywhere. It wasn't anywhere. It was the measurement that produces that particle at C. And then you have an agnostic position, which you refuse to answer the question. So I leave you these slides to which advocacy would um, favor. Are you a realist? Are you an orthodox, or are you an agnostic? So I leave it with you. But in 1964, John Bell surprised the physics community. He discovered that um, it's really the orthodox interpretation uh, was really the correct one, the correct position, according to him, according to his discovery. His discovery eliminated agnosticism and realism as viable options. And he said, a particle simply does not have a precise position prior to measurement any more than the ripples on a pond do. It is the measurement process that insists on one particular number and thereby, in a sense, creates the specific result limited only by the statistical weight imposed by the wave function. That's the orthodox interpretation, according to him. So when you do that experiment, you find the particle at C. After that, what if you do another measurement? Would C be the position of the particle? Or Does the act of measurement give some completely new number each time? Remember, the particle, as tiny as it is, the particle could be vibrating, is vibrating. And um, the moment you measure that, it is disturbed. And so C might not be exactly the C that you've measured before. So there is some kind of um, difference from one measurement to another measurement into another future measurement. But C would be, but it concentrates on the position C. We all have to agree that a repeated measurement of the same particle must return the same value. It would be tough to prove that the particle was really found at C in the first instance if this could not be confirmed by immediate repetition of the measurement. So you have to measure immediately in order to have a result that was measured in the previous measurement. Because if you spend time, uh, the probability of change is very high, and so you would get another value. According to the orthodox interpretation, the first measurement radically alters the wave function. So um, there is now a sharp peak at C. But again, according to this um, plot, uh, the particle is not exactly at C. It could be um, below C or greater than C. Then you have this plot. This figure is the collapse of a wave function. The wave function, the fashion of the wave function is supposed to be like this one, as it goes with time. By the way, I'm talking about the square of the wave function. As I say wave function, I'm talking about the square of the wave function. But in this case, it has collapsed because of the repeated measurements. So your wave function would look like this if you do repeated measurements. But if you don't do, the particle would, or the wave function of the particle would spread out again in accordance with the Schrödinger equation. So there are entirely two distinct kinds of physical processes. One is the wave function evolves in a leisurely fashion under the Schrödinger equation, and B, um, measurement in which psi suddenly discontinuously collapses. This one is a collapse of the wave function. Since we have been introduced by Max Born uh, indeterminacy in quantum mechanics, probability becomes a critical part of quantum mechanics. So we will study about probability. So you know about the wave function. I have introduced to you the Schrödinger equation. Now let's go to probability, because the wave function, the square of the wave function, is proportional to the probability. So imagine a room containing 14 people whose ages are as follows. One person aged 14, one person aged 15, three persons aged 16, two persons aged 22, two persons aged 24, and five persons aged 25. In that room, there are 14 people. Now we let um, j as our variable representing age, and then we have nj representing the number of people of age j. Then you can mathematically represent n of 1, for example, is 0, n of 2 is 0, up to n of 13 is 0, but you have n of 14 equals 1, n of 15 equals 1, n of 16 equals 3, n of 17, for example, is also 0, n of 18 is also 0 until n of 21 is 0, and then you have n of 22 equals 2, n of 24 equals 2, n of 25 equals 5, n of 26 equals 0, n of other numbers other than 14, 22, 15, 24, 16, and 25 is 0. So how would you get the total number? You have to add these n's to get the total number. In this case, the formula of finding the total number is this equation 1.4. So n, total number of people in the room, is just equal to the summation of nj, where j starts, or the age starts at 0 until infinity. Of course, n of 0 is 0 plus n of 1, which is also 0, n of 2, which is also 0, and then you until you reach n of 15 or 14 or 15, which are non-zero. And of course, as you go on to infinity, um, the total would just be 14. If you can see the plot here shows a histogram of the number of people in J with age J, for the particular example that we are discussing. So 14, 1, 15, 1, 16, 3, and you have 22, 2, 24, 2, 25, 5. The rest is 0. So question number 1. If you selected one individual at random from this group, what is the probability that the person's age is 15? The answer for that is 1 chance in 14, or 1 over 14. Since there are 14 possible choices and only one has the age 15, so that's 1 over 14. And we call that the probability of getting age j. So that's pj. So P14, P of 14 is equal to 1 over 14. P of 15 is 1 over 50, 1 over 14. P of 16 is of course 3 over 14, and so on. And Pj is just equal to Nj over the total number of persons. This is the number of persons with age J, and this is the total number of persons of all ages in the room. So that's the probability. So remember, you have more equations to remember. First is the Schrödinger equation, and then you also remember this one, and um, this one is the probability of something. That's just the number of occurrence of something over the total number of occurrence. This is the number of occurrence of that something that you want to find the probability of, divided by the total number of occurrences. Now, the probability of getting either 14 or 15 is the sum of the individual probabilities. In this case, this is 1 over 14, and this is 1 over 14. So the total probability would be the sum. This is 1 over 14 plus 1 over 14. So you will have 1 over 7 as a probability. The sum of all probabilities would be equal to 1. You should remember this. the sum of all probabilities is always equal to 1. So for example, Pj, j starting from 1, supposedly it should start with 0, but p0 is equal to 0, p1 is equal to 0, p14 is equal to 1 over 14, p15 is equal to 1 over 14, and so on. And when you add all those things, by the way, p of 26 is also 0. So when you add all the probabilities, it should be equal to 1. This is a rule. So the next question, what is the most probable age? The probable age is 25, since 5 people share this age. According to the histogram, this is the most probable age. This is 5 over 14, the greatest probability that you can get in the sample. So what is the most probable age? It's 25. The most for which Pj is a maximum. So for j equals 25, Pj is maximum at 5 over 14. Question number 3, what is the median age? The answer for that is 23, since 7 people are younger than it and 7 are older. The median is the value of j such that the probability of getting a smaller value of j is the same as getting a larger value of j. Are 7 people aging below 23, and there are 7 people aging greater than 23. Question number 4, what is the average or mean age? To do it, you just add these terms. So this is like 14 times the number of occurrence of the age 14 plus the age 15 times the number of occurrence, which is also 1, age 16 times the number of occurrence, which is 3, and then 22, which is possessed by 2 persons, 24 possessed by 2 persons, and then you have 25 possessed by 5 persons. So if you add this, you will get the mean age of 21 for all 14 people. So that's the mean age, that's the average. So remember, most probable, the median, the average, you should be able to tell the difference. So by the way, you can also write this as 14 times 1 over 14 plus 15 times 1 over 14 plus 16 times 3 over 14 plus 22 times 2 over 14 plus 24 times 2 over 14 plus 25 times 5 over 14. 1 over 14, 1 over 14, 3 over 14, 2 over 14, 2 over 14, and 5 over 14 tells you the probability. So this is just, if you write it in a mathematical form, you will have this. This is the average value of j. You can either use this formula, it's the summation of j times the number of occurrence of j divided by the total number n, or this is just equal to the summation of j times the probability of occurrence of j, where j starts from 0 to infinity. So in this example, no one has the average age of 21. The P21, P of 21 is 0, or the median age of 23. P23 is 0 also. But it's the average age and the median age respectively. In quantum mechanics, average of something is the quantity of interest. So the that is the quantity of interest in quantum mechanics. And the average is usually called in quantum mechanics expectation value. How does this value relate with the wave function? We will go further with the lectures on that on the relationship between expectation value and the wave function. It's very interesting, but it will be in another lecture. We will focus on probability for this lecture. Question: what is the average of the squares of the ages? Answer: you could get like 14 square plus with probability of 14, 1 over 14, 15 square with probability of 1 over 14, 16 square with a probability of 3 over 14, and so on. The average of the squares of the ages could be generalized by this equation. So here you have the average of j square is just the summation of j square plus pj, where j starts from 0 to infinity. Just like here, the average of j is just the summation of j times pj. So if you get the average of the summation of something times the probability of occurrence of that something, here it's just the same as here. And so in general, you will have the average of something, fj. So that could be j cubed plus j square minus 4j, for example. If you want to get the average of that function, then you would just use this formula. The summation of that function times the probability of occurrence of that function. So you have to also take a look at the j, because pj would be different for each j. So for example, in the example that we are discussing, p0 is equal to 0, so that's 0. So the function is not useful. But for pj, where j is equal to 14, which is 1 over 14, the function is useful. So you can get the average of this function. Fj could be any function or any something. The average of the squares, j square, is not ordinarily equal to the square of the average. This one, it's not equal. So beware of that. You have to remember that the average of j square is not equal to the average of j square. So in this case, in the example, in this example, for example, if the room contains just 2 babies, age 1 and 3, the average age would be 2. The average age would be 2. And if you square the 2, that's equal to 4. But the average of the squares is equal to 5, because this is 1 square plus 3 square, which is equal to 1 plus 9 equals 10, divided by 2 is equal to 5. So here, the average of the square is 5, and the square of the average is equal to 4. So they are not equal. In general, they are not. So it's also important to look at the spread of the distribution of the variables. So in this figure, you have a spread, a very small spread compared to this figure, to this plot, where the spread is broader, and this is kind of flat distribution but broad one. This one is like a spike distribution, but it's not broad. The number of elements are the same. The probable value 5 is the same. Here is 5. The average value is the same, and the same median age. So it has uh, the same characteristic, but the spread of the distribution is different. Aside from the average, the spread of the distribution is also important in quantum mechanics. So to do this, you have to first look at how the individual elements deviate from the average. You know the average here. For example, here is 5. Also, here is 5. But how about the other elements? You can get the delta J, where J is the could be the element minus the average of all the elements. So J would be, so delta J, if you do this mathematically, delta J, you have to put delta J inside here, the average of delta J. So anything that's inside here will be placed here. So delta J is equal to this, so that your delta J here would be uh, put inside the summation. And then you have JPJ. What is J? The summation of JPJ. This is just the average of J. This one, you have J. You can take this out because this is a constant in every data. You have the average. The average of the data is always constant, and you just have the probability to be summed up. And the probability, the sum of this is just equal to 1. So average of J times 1 is just equal to the average. And this one is the just the average of J by virtue of equation. So let's look at that again by virtue of equation 1.7. So you have the average of delta J is equal to 0. So it's a useless quantity to get the average of the deviations of the elements from its average. To avoid this, one can decide to average the absolute value of the delta J. The absolute value of the delta J are all positive. So you can add them and then you can get the average. That's that's a meaningful quantity. But customarily, it would be easier to get around the sign problem by squaring the delta J before averaging. And we define this as sigma square. This is the average of the square of delta J. So if you do that mathematically, by the way, this quantity, the sigma is called the variance. It's called the variance. And if you get the average of the variance, this is just this one, and then what's inside here, inside this grouping symbol like that, you have to put inside the summation times the probability. So you have this J minus average of J square, and then when you expand it, that's J squared times 2J times J, the average of J plus J, average of J squared, PJ. And then you expand it again. This one is just the average of the squares, this one, by virtue of um, equation 1.8 here. And then you have 2. Of course, J is a constant, so you can put that here. And then this one is also equal to the average of j. So this is j square plus j square here, because the summation of pj is equal to 1. So sigma square is just equal to j, the average of j square minus the square of the average of j. So this is now your sigma. 1.1, 1.11 is just equal to 1.12. But since sigma is always positive because it's a square, it's a non-negative. This implies that the average of j square is always greater than the square of the average. But they can be equal if all the elements have equal values, meaning there's no spread at all. So far, we are discussing an example which is discrete in nature. The variables are discrete, so they are just with values of an integer. How about taking variables that are continuous? We will uh, generalize this to continuous distributions in a moment. So, for example, if I selected a random person off the street, what is the probability of finding a person which has precisely an age of 16 years, 4 hours, 27 minutes, and 3.33 seconds? It's zero. It's it's impossible. I mean, almost impossible to find. But it would make more sense if I find a person between the age 16 and 16 plus 1 day. I guess I would find one if in a million of people, I guess, no? But this one is so specific that uh, the probability is almost close to zero. So if the interval is sufficiently short, the interval, meaning the interval, the dx in here, in this particular plot, if this is very short, this one, if that is very short, then the probability of finding is also very small. So, for example, the chance that her age is between 16 and 16 plus 2 days is presumably higher, or twice the probability that that to that of the interval 16 and 16 plus 1 day. So if you have a bigger interval, you have greater probability. A smaller interval would be lesser probability. But in particles, in quantum mechanical scenario, which are very small, the intervals are infinitesimal, very, very small. So the probability that a particle or a person or an individual chosen at random lies between x and x plus dx, this one is very small, is equal to some function rho of x times dx. This rho, this is the proportionality factor, which is called the probability density. This one, probability density. Rho x is probability density. And this is the probability of getting x. And so if you want to get the probability of x, I mean of a particle lying between A and B, or the position A and B, then you just have to integrate from A to B the probability density times dx, where the dx is um, limited only from A to B. So this is the probability of finding the particle from A to B. So you have 2 points. So this is for continuous distribution. We discussed an earlier example, which is um, for discrete distribution. For continuous distribution, the summation sign will be replaced by the integral sign. So for probability density, you can integrate that uh, from negative infinity to positive infinity, and the result would be 1. And so the expectation value also, whatever is here, should be placed before the integral. So you have x also here, and then the probability density times dx. You integrate that. And I'm sure you know how to integrate, or else you have to review your um, uh, integration class. So in this case, you also have, if you want to find probability, the average or the expectation value of something or a function, that function here inside this bracket, you have to put inside or before the integral sign times the probability density times the x. That's the expectation value of f of x. And then you also have correspondingly the sigma square. This is just x square, the average of that, minus the average square. This is the average of the square. This is the square of the average. So this ends the lecture, and in our Google room and in our Molly room, I will post some problems, but I could show you some of the problems here. Um, you can take a picture of that, and this is another problem. This is another problem. This is also another problem. Before we start with another topic in our next class, I will post some materials in our Mole classroom and in our Google Classroom. I will also post a problem set there so that you'll be able to answer those and submit to me. Thank you very much for attending the class.